Okay. So I will be, so my name is Peio Borthelle. I will be talking about operational game semantics formally, and specifically about the problem of chattering in composition. And this is joint work with my PhD advisors. Two of them are in the room, Guilhem and Yannick Zakowski. So first, a bit of context. So originally, at the start of my PhD, I was interested in looking at interactive semantics for foreign function interfaces to see how languages interact with each other, crossing abstraction levels and stuff like that. So we decided on using operational game semantics. And so step one was to build a model and prove soundness. And formally, because I really like mostly programming, I like proving stuff, but more if it is using dependent types. And so after some point, I realized this was kind of tricky. I couldn't really just brute force the proof. So this is the statement I'm looking at. I want to, I have two programs, P and Q. They are bisimilar, equivalent in my model. And I want to prove soundness with respect to contextual equivalence. So for any, this is a variant of it with evaluation, context, and substitutions. So I want to prove that in any setting, they evaluate to the same value. So the problems I encountered are of two parts. One is you have to formalize syntax, so binders, types, stuff like this. This can be tedious, but this is well studied, and I'm not going to go into too many details. The part I want to focus on in this talk is the subtle co-inductive reasonings which occur when you define game semantics or the operational game semantics I'm interested in. And so some key choices I made. So for example, I think something which is important is that I'm using a well-scoped approach to binders. So it's an alternative to nominal approaches, which I think are more common in this community. It also works. So we axiomatized a bit from a concrete syntax to keep the syntactic details separate and only keep what is relevant. And also, we used some category style to formalize LTSs. So the outline, I'm gonna go quickly and see what my operational game semantic looks like. We have seen some already. And then I'm gonna go into composition and some mystery. And I will conclude with some remarks on recursive equations in iterative monads. So let's get to it. So at the heart of interactive semantics is the notion of interaction. And so we have these two players which are asking questions to one another. So this is what I'm calling observations. And so at different types, there will be different kinds of questions you can ask. So for a function, you can apply it to some value v. And so notice I also give some kappa, which stands for a continuation. So this looks a bit like a continuation passing style. So for a pair, there are two observations, first and second. And what is fun is that in this continuation passing style, answers are just a particular kind of questions. So there are questions you ask to a continuation. So something you can observe or ask to a continuation is, what do you do if I give you this value? And it won't return to you, so you jump to it, basically. And this is actually a notion of copatterns. So in practice, the languages I'm looking at are pure, but they may have a divergence. So in type theory, I'm using the delay monad, which is a co-inductive monad, which has basically two operations, returning or a step, a silent step. And the operational semantic is, I forget completely about terms, and I focus on configurations, so some sequence calculus style language. So we have values which are well-typed and well-scoped, configurations which only have a scope, they don't have a return type, and these observations. So we have an evaluator, which is a monadic map from configurations to normal forms. And what is fun is that we can, normal forms are not given to us. We require them to be triplets of a head variable, which we are stuck on, an observation on it, and some arguments in green, which fill the holes of the observation, so the arguments. Because in this interactive semantics, we usually want to hide away the arguments. They are not crossing the player boundaries. And so in this sequence calculus setting, this is the definition of contextual equivalence I will take. So it only mentions substitutions and not evaluation context. Now the semantics, the operational game semantics on top of this, which we build, are basically labeled transition systems. Here I'm not going to go into too many details. This is following work by Paul Levy and Sam Staton, where they represent the LTSs in two separate sets of states, the active states where you play a move. And so you have the first play transition function from active states to eventually a move, so an observation, and some passive states. And the passive states, for which the transition function takes a passive state and a move which was played by the opponent and gives the new active state. And so this is the whole set of strategies of this kind, but operational semantic is about one particular strategy coming from our operational semantic, so from the evaluator. And so in this operational, what I'm calling operational strategy, the active states are a language configuration and some suspended values, which we don't want to give to our opponent. And the passive state are just the suspended values. And so to play, we evaluate our configuration, and we obtain a normal form. We keep only the head variable and the observation, and we hide the arguments. And coplay is a function which will apply, which will take a value and apply to it an observation. So yeah, and we also use interaction trees in the Coq formalization, so a slight tweak on the co-algebraic style. So what about composition? So why are we doing composition? So we wanted to prove soundness, and the standard approach in operational game semantics is to prove, so first a usually simple fact which composition respects by similarity, and the important fact which I call adequacy is that composition simulates substitution. So we introduce this composition of an active state and a passive state, which gets to a final result, and this should have verify the first line. So evaluating a substituted configuration should be the same thing as interpreting in our model and then using this kind of semantic substitution, so composition. And then we have a simple derivation of the soundness proof. So characterizing composition. Composition so takes an active state and a passive state in a matching position. And first, the composition is defined by evaluating the active part, getting the message, and then passing this message to the other side. There is a case split here because there are some variables which are final variables which end completely the interaction. The problem is that this is in fact not a co-inductive definition because Coq doesn't accept it, so at least it's not a Coq valid co-inductive definition. And the problem here is that there is some bad looping which makes this not defined in some cases. So a classic looping example is that we have a configuration which has ended its computation, it's true, and it returns to some channel return continuation x. And the opponent says x is some y, which you know, and we say, oh, y, I know it, it's x, which you know. And so then we can easily imagine the composition of these two configurations will be an infinite loop without any reduction steps. So this is a known problem, but with a slight twist. So it is known that two processes sharing a bidirectional channel can stop interacting with the world, but for it, it's fine if they do some reduction steps. It's not fine if they just keep saying it's your turn. So now the rest of the talk will be playing hide and seek to find some reduction steps in this composition to see why it is well defined. So the first thing we will notice is that usually this kind of loops, x points to y and y points to x, cannot happen because there is an order in which the variables were introduced. So the time order. And so the two scopes of my variables and your variables, they actually form an acyclic graph. And by representing them not as pairs of context, but as a sequential interleaving of each of the context extensions, we can have a better phenotype. And so we can, using this, we can refine the suspended values, so the assignments, with some really beautiful mutual inductives, which I don't have given the typing rules. So basically, we have these two parts of the interleaving, and the player environments will mention variables from the opponent's scope, but only older, and this enables us to show that when we substitute iteratively, at some point we will end at the bottom. So we have some finite chattering, so saying, no, it's your turn. This eventually it ends either with a complete stop in the final message, or some head variable is replaced by a proper value, a value which is not just a variable. So this is good, but this is still not enough to find a redex, because, for example, if you start with an unknown function, which you should return to an unknown continuation, then after the first sequence of chattering, you will instantiate y with a proper value, but this is still not a redex. You need a second step to get a redex. So, and in this example, we need two, but we don't know. Since we axiomatize the language, we know nothing about the length of these interactions. So the mystery hypothesis, it's just defining the relation of such head instantiations that don't produce a redex, and saying at some point it does produce a redex. So this hypothesis is kind of, I called it mysterious, because it's really hard to think about a language in which it is not true, like in two steps. But at the same time, if we axiomatize stuff, we cannot prove soundness without this. Sorry. And so I call it finite redex because, in some sense, this is coming from the fact that redex have two parts. And so to conclude with eventually guardedness, so how does this fit in our theory? So I have explained informally how to find a redex at some point in the trace of composition. But how does this help us with our definition? So, in fact, the construction which is happening here is computing fixed points of monadic maps in the delay monad, and so recursive equation can be represented as monadic maps where you have some set X which you think about as variables, and Y which is the final results. And so we say we have some zoo of guardedness criterion which enable us to take fixed points of these maps. And the simplest one is that an equation is guarded if it is not just saying start again with some other input. So if something happens before the recursive call. And as we have seen, composition is not guarded because sometimes you do nothing and say, oh, it's your turn. But in fact, it's eventually guarded in the sense that after some finite amount of steps, so every so often in the loop, you will get a guard, so some operation going on. For us, it's operational reduction steps. And so you can recover the existence and unicity principle of the equation system. And the unicity principle is, in fact, the most important because this is what enables us quite straightforwardly then to prove adequacy of composition with substitution. And so to conclude, the main contribution is a formalized generic soundness theorem for OGS. And so generic here means that we cover some sequence calculus style calculi, basically, so we have proven it for some polarized and non-polarized versions of mu tilde and lambda calculus, and some new, I'm not sure it is new, this eventually guardedness criterion, so if you know more about it, I'd be happy to know. Thank you.
We have time for one or two questions, yeah?
Thanks for the talk. This eventual guardedness reminds me of something. There is a concern that it could be undecidable. So usually you would want to check guardedness, right? There was a paper in GALOP'22, I think, by David Bald, Amina Dumain and others. And they saw that there is this sort of eventual guardedness. Well, not exactly the way you do it, but they found that if you do not have an explicit bound, you say like you check up to some n, then it turns out to be undecidable.
Yeah, so I don't know the work you mentioned, but so here, in fact, in the formalization, it's not a natural number. I have an inductive predicate, and so it's all, there's no checking involved. It's the user, so in fact us, which are providing the proof that after some point, indeed, a guard is obtained, and so the composition is then not a co-inductive definition, but a co-inductive definition with inside an inductive definition.
So my question is about the mystery hypothesis. So is it an hypothesis in the Gauss sense? Something that you... So I think it might relate to some issues that we have in concurrent game, causal game semantics, where if you're not, where there are deadlock issues in the composition. And in some instances, for some languages, you can show that these deadlocks actually don't occur.
Yes.
And I'm wondering whether we could, you could use these kind of ideas to show the mystery hypothesis under reasonable assumptions of the language.
Yes.
It's more a comment than
yeah.
This looks familiar.
Okay. It's really weird for language not to have it. It would have to have one rule which is infinitary in some way. So
maybe we can discuss it online because I have plenty nice, but then there are
Yeah.
plenty of languages which do not.
Oh, okay, okay. Then, okay.
Yeah, thanks again.